Okay, so for geometry today, we've got section 4.4, applying congruence postulates. So some fun stuff. Why is my screen? Oh, okay, I'm good. It's just my board is messed up. All right, I'm talking to myself, except I'm not. It is broken-ish. All right, so we have a new theorem today, new congruence theorem. So this one is angle, angle, side. Let me get a different color that sticks out a little more. Angle, angle, side. Okay, so this one says if two angles and this time says non-included side. So we want the angle, the next angle, and then the next side. Okay. So two angles and a non-included side of one triangle are congruent to the corresponding sides, angles, and side of another triangle. Then the two triangles are congruent. So we're proving triangles congruent by an angle, angle, side. So here we have angle A is congruent to angle X. Angle C is congruent to angle Z. So that's our angle, angle so far. Right, angle, angle. And then we have side AB is congruent to side XY. But it's non-included. It's not the side in between the two angles, right? It's one of the other sides. So that's our new theorem today is angle, angle, side. Okay, so example 1, this is called a flowchart proof. Okay, so I'm going to move this so we can get the whole chart proof up there. And let's take a look at it and make sense of this flowchart proof. So we're given that OM is a perpendicular bisector of LN. And we want to prove that triangle LON is isosceles. What's an isosceles triangle? What's an isosceles?
Two sides are equal.
Two sides are equal. Okay, so we want to prove that two sides are equal. All right, so we take this idea that OM is a perpendicular bisector of LN, and we write, well, that's given. So my statements are circled. So the next statement I make says, hey, M is the midpoint then, right? M has to be the midpoint of LN. And that says that's the definition of a bisector. Well, knowing that, LM is congruent to MN, or NM. And that is because the definition of a midpoint. So you can track a little bit. Here we had the word midpoint. We got this, and midpoint came into our definition down here. Okay. Here we had bisector, and that was, we used the definition of bisector there. Okay, so those are coming into play. So we just proved that LM is congruent to NM. Are we good so far? Okay, so I'm going to undo the last, and did you understand what I was saying here about like bisector? Oh wait, we use that. Midpoint's important. The definition of a midpoint told us something more. Okay. Okay. All right, so let me take those out of the way. Let's look at the next train of thought that we have here. Okay, so also from this given statement, we could say, well, since it's a perpendicular bisector, we know angle LMO and NMO are right angles. Right, we know this is a right angle and this is a right angle because it's again, they're perpendicular. The reasoning is it's a definition of perpendicular. Okay, we're using that terminology. All right, I'm going to get that out of there so it's less confusing. So now we say, well, hey, they're both right angles, so angle LMO is congruent to angle NMO because all right angles are congruent. And then we can say, well, then triangle LMO is congruent to triangle NMO. Well, wait, we haven't proved that yet, right? We have one side and we have one angle. So then they're like, but we know we brought this last piece in. OM is congruent to OM. All right. Yes. Okay. Because of the reflexive property. So we have a side, an angle, and a side that are all congruent. Or sorry, here was the angle that was congruent. Here's the other side. So now all three of these pieces come together to say that the triangles are congruent because it's side, angle, side congruence. It is a sassy triangle, a very sassy triangle. All right, so then we kind of changed gears. Now we're saying, well, OL is congruent to ON. Okay, so OL is congruent to ON because we have corresponding parts of congruent triangles are congruent. And so now we can say that triangle LON is isosceles because we just proved that two sides of that LON triangle were congruent, which is a definition of the isosceles triangle. Two sides have to be congruent. And again, this is called a flowchart proof. Can you use that? Yes. We are going to use them. Yeah, so we are going to do some flowchart proofs, and you'll see them in the book as well and things. So I want you to recognize them. It takes a little bit of practice. Sometimes it's nice because it's like, oh, I can see where one train of thought leads and then where another train of thought leads. And then you have, you might have a third or a fourth and where it pulls in. And it's nice to see like all three of these is where we get the side angle side. So it's kind of nice at times. It might help you understand like a two-column proof better, but that's our flowchart proof. Boo. Okay. Could be. I understand. Geometry is different. It's just different. Okay. Next up is the isosceles triangle theorem. So if two sides of a triangle, so if we have two sides of a triangle are congruent, this is the fun one. The angles opposite those sides are congruent. Okay, so they're called the base angles. So in this case, we have side AB is congruent to side CB. Do you agree? That's what's marked. So what angle is opposite of AB?
C.
Angle C. So you need to mark that on yours. What angle is opposite of CB?
A.
A. Because we know if two sides are congruent, then we know two angles have to be congruent. And the angle relationship, angle side relationship, is always the opposites. So let me give you another one. Okay, let's say these are equal. All right, what angle is opposite of XY? Z. What angle is opposite of XZ? Y. Correct. Okay, so what angle is opposite of YZ? X, but it's the one that's not congruent, right? It would be more of closer to a right angle. All right, perfect. So it's always a side angle, like opposite side and to the opposite angle. That relationship is there. Okay, fantastic. Let's keep going. Okay, so another one I've got, we're just going to walk through the proof together and talk about it because this one has the auxiliary line put in it. Okay, so this is the first one we've had with that. So if we're given the isosceles triangle XYZ with XY congruent to XZ, so that's marked, we want to prove angle Y is congruent to angle Z. All right, so first we've got our given. XY is congruent to XZ. All right, then step 2, this is the tricky, like we haven't ever had this before. It says draw XW bisecting angle YXZ.
What's the point of drawing?
Okay. Okay, so pull out, it says the protractor postulate. So I want you to get that and pull it out. What is the protractor postulate? The protractor postulate. Somebody is bitter today.
An angle A.
Okay, can you tell me the number so we could all find it?
1.5.2.
1.5.2.
Placed in a 1-to-1 correspondence with a degree measure less than or equal to 180.
Okay, so I'm going to read that again. Any angle A can be placed in a 1-to-1 correspondence with a degree measure less than or equal to 180. All right, so we can and this is bisecting. What does bisecting mean?
Going straight through the middle.
Going straight through the middle, which means it does what?
Splitting it in half evenly.
Okay, it splits it in half evenly. Okay, so that's where we went from 2 to 3. We could say angle YXW. So YXW is congruent to angle ZXW. So ZXW. W. Okay. Because of the definition of an angle bisector. So
do the opposite angles too? Because of definition of bisectors, can't you do the two angles of W?
you cannot.
Why?
Because so the protractor.
No, you wouldn't be able to know.
No, not necessarily, because we're dissecting. Not with this theorem. That has more to do with the fact that it's an isosceles triangle.
For W?
Yeah, because if we had an angle like this, that's going to end up looking the same. Like this, we can bisect this angle to where these are the same, but it's not going to tell us about these. Do you see that they look a little different?
Yeah.
Okay, so what you're stating is more of a relationship to the fact that these are isosceles angles, or like it's an isosceles triangle, than that. So it looks more like it, but it's not necessarily. The protractor postulate does not prove that. Okay, good point. All right, so we're able to say that angle YXW is congruent to angle ZXW. And then we've got XW is congruent to XW. Okay, so if we actually made that a line, and so that's that reflexive property. Because we've split this triangle into two parts. All right, well, with that, we've just proved a side, an included angle, and another side are congruent. So we can say that those two triangles, right, it's a SAS triangle. Triangle XYW is congruent to triangle ZXW. And now that we know it's congruent, we can say, hey, angle Y has to be congruent to angle Z because corresponding parts of congruent triangles are corresponding.
Oh yeah, because we already knew the other.
Or are congruent. Mm-hmm.
We had information on all the sides once we had the bisector.
We had information on all the sides once we had the bisector. W would be the midpoint because it's an isosceles triangle. Mm-hmm. Okay. So again, just wanted you to see that like how this protractor postulate kind of plays out, and you can draw in an auxiliary line and give reason for drawing in that line. In this case, it was a bisecting line. All right, next up then is the converse of the isosceles triangle. What was the isosceles triangle theorem?
Basically, if the two sides are
congruent,
then the opposite base angles are congruent also.
Okay, so the converse means the opposite, right? The isosceles triangle theorem said if two sides are congruent, then their opposite angles are congruent. This one says if two angles of a triangle are congruent. But again, we're starting with the angles this time. It's the converse. Then the sides opposite those angles are congruent. And, so this one's got two parts to it, the triangle is isosceles. So if angle A is congruent to angle C, okay, is what we're looking at. So what's the opposite side of angle A? Okay, so opposite is the side it's not touching. Okay, it'd be CB because angle A touches AB and it touches AC. So the opposite is the side it doesn't touch. Okay, what side is opposite of angle C? AB. So again, it's like opposite. You can usually draw a line straight over to them.
Is this still recording?
Yeah.
The little timer.
Yeah, the timer disappears after like 10 minutes or something. Okay, so questions about the converse. Okay, it's just going backwards, right? All right, we have another little theorem down there then. Theorem 444. Oh, it's really simple. Oh, this down here? Don't get there yet. Okay, so here, this theorem is more just a phrase that you would use. So a triangle is equilateral if and only if it is equiangular. So you can write it in a proof like either of these ways, right? Equilateral means it's equiangular. If it's equiangular, you can say it's also equilateral, right? Like that's just the deal because we know that those relationships, right? What's the opposite of this angle? Hold on, let me see. A, B, C. So all three of them are equal, so it doesn't really matter. But if it's all three angles are equal, all three sides have to be equal, and vice versa. All right. Now, many proofs involve overlapping triangles. Okay, the way to solve this is to draw separate diagrams of the triangles. So this is what I'm showing you. Okay, so in this one, we have this TER triangle. Okay, so I pulled it out, drew it over here, and angle 2 is part of that triangle. And then on the next one, okay, we have angle DST. Angle 1 is part of it, so I pulled it out and drew it over here. Are they perfect? No, it doesn't matter. Okay, but I've separated them out so I can see them. I've put the markings in there that show, hey, angle E is congruent to angle D. That's what matters. And we can go from there. And we can also tell, so maybe we wanted to say, we wanted to prove that triangle TER is congruent to triangle what? How would you name that one? TDS. So remember I also talked about like in naming these, like, okay, the T's match up, the D matches here, and R and S would go together. So you can do the same thing here. This would be T and E, and this would be R. So when you're trying to compare them, you kind of have those letters together so you know what you're comparing a little bit easier because you're like, okay, TE is going to be congruent to, oh, TD over here. Okay, so you can, there's a couple different ways, but it's just a matter of helping yourself see the shapes because that's what we're really going to be doing on the next two things, is we're going to be doing two proofs. But you have to see the shapes. The first one, okay, example 2, I pulled the shapes out for you. We've got the given and we want to get through our proof here. So we're given, do you guys see how I went from the one combined shape to down here?
Yeah.
Pulling them apart? Okay, and then I went ahead and marked them. So angle A is congruent to angle D. So I'm going to write here D though. And angle, triangle ABC goes with triangle DCB. Okay, so I'm just looking at the naming, and A lines up with D, B lines up with C, and then C lines up with B over here. Okay, so I know I would have to flip them.
B lines up with C.
Oh, B lines up with C. Thank you. I wrote B again. Well, I wondered, I was like looking at it, I'm like, something doesn't look right. I couldn't figure it out though while I was trying to talk. Okay, so if we want to prove that AC is congruent to DB, and we've got two angles congruent, any ideas of what we could do? Okay, we just learned a new theorem today. What was our new theorem?
Which one?
Isosceles.
4.4.4?
No, this is an equilateral triangle, but good try. What was it, Justice?
The converse of the isosceles triangle.
We don't know anything about these being isosceles, though, so that one wouldn't be helpful.
Angle side, angle congruent.
Angle side.
Angle side.
That's what I said.
Close. Okay. So there is angle side. So does that mean that we have to prove this side congruent?
No.
No, we don't, because looking at this picture, I don't know how we'd prove them congruent. So we don't want to do that. Can we prove any side congruent? Any side. AC and DB. That's what we want to prove. But is there any side right now that we can show are congruent?
ABDC, because it's a side between two angles, which means you already know it. It's
Wait, AB. What?
I don't know.
Okay, so can we prove AC is congruent to DB? Like
wait, no.
CB and BC?
Yeah, because
Okay.
it's the same.
Yeah, there we go. Okay, because we can't prove these congruent. Like there's no relationship up here that shows me they're congruent. But we can prove these two congruent. Why?
Because they're the same.
Because they're the same when?
When they're connected.
Okay, so if we look back here, right? Like, look, when they're stacked on top of each other, we see that they're the same. So, yeah, so segment BC is congruent to segment CB. Lucas, what property is that?
Yeah, Lucas. No, at this one it'd be an S, wouldn't it?
I would take either one. Do you want to give me reflexive or symmetric? Yep, I would take either one. So this is the reflexive property of congruence. Good. All right. So now we've got an angle, and a non-included side. What's that mean I can say about these two triangles? Angle side is my angle side congruence says what about these two triangles?
Oh, the triangles are equal.
Doesn't say that they're equal.
Yeah, the triangles are corresponding. Dang it, now you got me saying weird words. Congruent.
All right, it says that the triangles are congruent. So Justice, give me a congruence statement. So triangle.
How would you label it? A, B, C?
I would label it the same way they labeled it right there. That's a good question. I would just call it triangle. Uh-huh.
Congruent to triangle DCB.
Excellent. That's our congruence statement right there.
Excellent.
And so what's our reasoning now? Segment AC then is congruent to segment DB. So AC. Okay, corresponding parts of congruent triangles are congruent. CPCTC. Whoop, whoop. That's good. Very nice. Okay, so example 3 then. You need to take some time and draw your separate shapes out.
Is there 4? No.
Is there 4? That's a good question. Okay, so let's look at it. VW is congruent to VX. Triangle WVQ is congruent to angle XVQ. Prove that VR bisects angle WRX.
Dude, I'm so confused. Can you go through this with us?
Okay, so what?
What would we draw here?
Okay, what would you draw here?
Something.
Something? I mean, you technically wouldn't have to draw anything.
Okay. Alright, now since we didn't draw anything, what's our next step?
Okay, so do we want to just try without drawing anything?
Yeah.
And see, because this one has like 4 parts. I get that. Okay. So let's mark it.
Are you really trying to only pay attention to the smallest two? Or do we need to know the other two big ones?
Well, and here's the other thing. You can always start it without drawing 2 separate ones, or like separating them out, because like this one is more confusing. And then as you work your way through, maybe you see like, oh, okay, now I need to draw something to help me out. That is okay. That's probably how I would tackle this one too when I really look at it. So let's mark it. When it says VW is congruent to VX, Justice, what would you go up and mark it? What is that saying about the shape?
What?
That first one, VW is congruent to VX.
Little picture.
Uh-huh. Yep, go mark it on the picture, on the diagram. Lucas, you're next. So the angle, where would you mark? Time out, it says they're congruent.
The little line.
The little line, yeah.
Do I have to push this button?
Nope, you don't push any button. Just write on it. There you go.
That's awful.
Yeah.
Okay.
VW is congruent to VX.
I don't know.
That's it.
In the center, but I don't
That's okay. It doesn't have to be in the center. Okay, so that tells us our segment congruence. All right, Lucas, what about our angle congruence? WVQ is congruent to XVQ. I like it. Color change even.
WVQ
Uh-huh.
is congruent to what?
It says
Right.
X.
XVQ. So where's WVQ? WVQ, that angle. So WV to Q, so the angle right in here. There you go. Is congruent to XVQ. So XVQ. Well, so X to V, that's the vertex to Q. So where would it be? Yep. There you go. All right, perfect. All right, so we got that marked. I might clean up our marks a little bit here, actually. Okay, there we go. So we have a side, one side, and one angle that are congruent. Okay, can we prove any other sides or angles congruent?
No.
By looking at it, you can.
By looking at it, I can? What can I prove congruent by looking at it?
I mean, like you can obviously tell, like in the future, that like the WR and XR are gonna be congruent. I feel like.
Okay, you feel like that, but can we prove it?
Yeah, but I feel like eventually you'll be able to.
Eventually we'll be able to. Okay, if we look at it, is there anything that we're like, oh, well, these are definitely congruent?
Oh my gosh, yes, the VQ line.
The VQ line? Okay, so
The VQ and the QV.
so here's a question for you.
No, they're both VQ, and there's
Because we want to prove VR bisects WRX, do we want to say VQ? I mean, we can do both. We could say, and get it in there, VQ is congruent to VQ, but we could also say VR is congruent to VR.
Well, we're only trying to find the triangle. Oh, never mind. I don't know.
I'm trying to find VR.
Okay, so that's what I'm saying. Here it does say VR, so we want to prove something with VR. Okay, so both of these are going to be helpful, but what's the reason for that then? That we've got VR is congruent. No.
They're supplementary or not?
Not supplementary.
Symmetric.
Symmetric. Okay, so symmetric or reflexive. Which one do we use on the last one? Reflexive. Okay. Again, it doesn't really. So we'll stick with reflexive. So the reflexive property of congruence. All right. So now might be a good time to pull those out
Give me that.
because we've got triangle VRW and we have triangle VRX here, but we know this angle is congruent to this angle. We know this side is congruent to this side, and we just said this side is congruent to this side. So now if we pull it apart, we can say, oh wait, we've got side. What do we have in there? Side angle side congruence is happening. So what's that say about the angles? Or the triangles, pardon me. Give me a
the triangles are congruent.
what you have to name them though.
Triangle VWR is congruent to EXR.
Perfect. Okay. So now we've got triangles are congruent, but we're still trying to prove that VR bisects angle WRX. What's the okay? So it's going to be important that we have this word, this definition of bisects. What's a angle bisector? Cuts it perfectly in half. All right. Well, we've kind of already proved that it cuts this perfectly in half, right? Because they told us these were congruent. But in order to bisect WRX,
CPCTC for a line WQ and QX and XQ.
we don't care about WQ and QX.
No, but it'll help us.
Okay. All right. So
WRXR CPCT.
WRXR. Okay.
Oh no, it has something to do with CPCTC.
It does have something to do with CPCTC. But in order to prove that it's it's true. We want to prove that the angle, it's an angle bisector. Right? We want to prove, so think about this. We said, we knew these were congruent. Okay? So, and the definition of an angle bisector is that it cuts an angle, right? An angle bisector takes an angle. So if this angle is 60 and it cuts it in half, what is each of these angles now? 30. Okay. But here's the deal. This is what's happening. Now we have this other shape over here. What's happening to these angles? What do they have to be? They have to be congruent. Maybe they're 40 each, which would make this whole thing, this angle, how many degrees? 80. But in order for this to be an angle bisector, for this dash line here, to be an angle bisector, these have to be congruent. Do we know if those are congruent in ours?
Yeah.
Why do we know that they're congruent? Are we following this though? Okay, we've proved the triangle is congruent. So we know that we can say, well, hey, WRV is congruent to XRV. So we can say angle W, right? WRV.
What? WRQ? I did Q. I don't know why.
Okay. Is congruent to angle XRV because of corresponding parts of congruent triangles are congruent. So now that we've proved that, okay, so this is our angle. Let me clean this up maybe, because that's really what we want. We've proved that this angle is congruent to this angle, and we've proved that this angle is congruent to this angle. What does it make VR?
Perfect bisector.
A bisector, right? Because it bisected angle V perfectly, it cut it in half, and it cut R in half, angle R. So we can say that VR, segment VR, bisects angle WRX. And why can we say that?
Bisecting
Definition of an angle bisector. Yep. So angle bisector. It's going to be the definition of an angle bisector because it had to cut both of those angles in half. So we have to prove that that this pair of angles is congruent and this pair of angles is also congruent so that we could say, hey, it bisected the whole thing.
And no homework, correct? Correct.
False. Always homework.
Are we gonna do this on Thanksgiving week?
Yeah, I'm going to give you homework on Thanksgiving week.
Please don't give us
I don't know about tomorrow. All right, questions about this proof?
We're gonna have a fun day tomorrow, right?
Okay, then I'm going to leave this up so you can get it. Your homework is on the front there, that page 172 to work on, and we'll see you tomorrow.